Let's get started. Hello, welcome back to the last session. So first we have Ce Liu talking about layers. Take it away, Ce.
Well, thank you, Vincent. It's my great honor to be here to celebrate Ted's 70th birthday. By the way, this title is actually from Yair. And he asked me to present first 20 years of layers. I'm like, wait a minute, 30 years of layers. Obviously we live in a living world, even though in computer vision, mostly we have been processing images. But just we see videos all the time. Our eyes have been seeing videos all the time. The classic formulation of motion is optical flow, and Adelson gave a great talk today in the morning about optical flow. And if you look at the flow, the history of flow, they've been like almost 40 years, and the most recent one, I think the classic one is from De Qing, right? De Qing is sitting there. This from Sunrise and Black got the test of time paper award at CVPR, 2020. I think optical flow has been there for 40 years. This great achievement. When I came to MIT in 2003, Bill and Ted, my co-advisors, they've been telling me, okay, why don't you work on motion? I think this sounds very interesting. And Ted told me the trick to really, use the flow field, right? Warp the second frame to the first frame, and to check whether they match. And if they match, right? So on the right, you can see it's actually animation, right? On the left, you see the animation of the input 2 frames. And clearly you can see the motion, and on the right, you can see some subtle motion here and there. That means wherever you see subtle motion, actually that means the motion the flow estimation is not correct. And that's the kind of the status of flow. And flow is really in many ways is amazing. I mean, you can do especially recent days, you can do a pretty amazing optical flow estimation. But Ted was my thesis co-advisor, and this is my wedding picture, and I have my wife and my daughter here. This picture was taken in 2009. Ted has very unique eyes and very unique thoughts about pretty much every problem, every question. And for Ted, what is really motion, right? So what do you see here? You see probably something's moving in a circular way. But if you slow it down, what do you see, right? It's actually it's simply a light, a string of light shooting on a surface, right? So if you were asked what's the motion of those pixels, right? You can say you can stay with the background, right? Because we have a static thing here, really. Nothing. There's no physical movement, right, of anything. But the light is moving. So if you follow the light, right, every pixel that's been lighted up, you can also, it has the motion of the light, right? So what's the optical flow? Because in optical flow, that notion, right? So one pixel is assigned with one flow vector. But here you're really facing, we probably want to assign 2 flow vectors, right, for a pixel. So I think Ted has been really thinking out of the box. The convention of flow representation is not the most satisfying way of representing motion that we see. And I think that's really true, because if you look at the real world, right, so you see a lot of the motion is caused by just very complex, can be caused by, of course, the motion of the objects, and also motion of lights, and you see a lot of motion blur, all kinds of issues. And there's even some sort of untouchable areas. It's really hard to estimate the motion of fire, of water, of clouds. I mean, those are still very hard to do motion estimation. In 91, that was before, right? It was about 12 years before I arrived at MIT. Ted has this brilliant idea of layer representation for image coding, right? That he really felt like image is really composed of multiple layers. And he gave a very good example here that there's background, foreground, there's this background alpha and foreground alpha, that you can compose them together, and you can make an image. And that's really a brilliant way to think about the imaging process, and also how we can in the following years, right, there was a paper from Wang and Adelson representing moving images with layers, right? So that's really I think, the first work to be able to expand the notion of layers into moving frames. And the key idea here is, first do some motion analysis and you do some clustering. So you can basically cluster, for most of the things, you have 2 or 3 dominant motions, and you can just cluster them and then get the layers. And of course, right, there's the segmentation problem. The problem becomes fairly complex. And there was a brilliant solution at the time, and it works pretty well for this classic flower garden example. That you can run the system and decompose this input sequence of flower garden into the background layer and the tree layer, and you get the motion of each layer and also the alpha mat and also the appearance, the pixels of each layer. I think this was brilliant almost 30 years ago. And following that, Yair and Ted really pushed this into a new level by introducing EM algorithm that formulated, I think this is a formal formulation of layer estimation that you have to go back and forth between motion estimation and grouping, and you can really get the motion correct for very complex things. And when I came to MIT, we started this project, motion magnification. Fedor already showed some demos that basically we were working together to do this motion representation and layer segmentation, starting from feature tracking. Once we know the tracks of the feature points, we can do some sort of clustering and know the number of layers, and then do segmentation, all those things. I mean, nowadays you would think, okay, we should do everything in one neural network. But this was almost 20 years ago with all the handcrafted features and sort of design systems. And it was working pretty well. You can see the power of layers that we can magnify the motion of the swing set and also fill in the pixels of the background, right, and get this motion magnification effect. And then we moved on and we found that layers can be also useful to help humans to label moving objects in the scene. That we can, in this paper, what we found is we can use layers to help to label ground truth motion, right, to have human and computer work together, because human is good at identifying objects and the occlusion relationships, and computer is able to get the flow field for every layer. So we did this sort of bi-layer flow estimation and then put everything together that we can get some sort of a pseudo ground truth of optical flow for very complex things. I think Ted is really interested in really a very broad sets of representations for motion, right? So layers, of course, it's all about pixels, about alpha matting, but also we can do layer estimation on contours. And for some examples, such as on the left, those on the left, it will be easier, right, to analyze the motion of the contours. And I think one Ted's favorite subject is about T-junctions, about the motion of the junctions that typically wrong, right? You cannot, because if you took a computer vision class at the time, well, what you learn is you trust the motion of the corners of the junctions because the motion is very strong. There's no aperture problem, so you should trust the motion of corners. But Ted is always saying, we cannot trust the motion of those junctions, right? Because typically, it's the motion of the junction alone. Those are wrong, right? There are really two motions presented in the scene. So we did some work to analyze motion of those scenarios. And then we moved on. It's sort of interesting, right? So if you're in this field of motion analysis, layer is, I didn't feel layer was a mainstream research topic. Still, most of people working on, optical flow, this pixel-wise representation. For good practical reasons, because for most of the things that people care about, optic flow seems to be sufficient. It's actually often it's on the computational photography side when we need to reconstruct images that this layer-based representation becomes very handy. All right, this is a case. This is a paper with Tianfan, Mickey, and Bill. Too bad Mickey cannot be here today. That we did this obstruction-free photography. We're using layer-based approach. See, right? So you can see that here we can simulate the user, right, using a phone, taking a sequence through a window, right? Here's I believe this is Tianfan's shirt, that you can see sort of, the disparity of the motion of the reflection layer and the background layer, right? And this disparity is an important cue for us to separate those two layers, right? So as you can see, right, so from this input video, if we align respect to the background, right, you can see on the left, the background is static, and we can do some simple Poisson reconstruction, can kind of remove the reflection layer, or we can fix the reflection and we can remove the background. Right, so those are the kind of simple approach to be able to decompose a scene, right? Because I don't know whether you've been to, check into a hotel, right? You look at outside this fantastic view, and you want to take a picture, right? And just often, just because the internal lighting is too strong, it's difficult to take a nice picture of through the windows. And here we provided a technology to be able to do that. Right, so here we show the before and after, right? We're able to do a pretty clean reconstruction. And also this technology can also be applied to remove fences. Right, here's, fence in the Boston Zoo, and now we can remove the fence. So, and those are sort of technologies, before the neural computing era. I want to shout out for this paper, right? This is a paper by Erica, Forrester, Tally, AZ, Bill, and Mickey. It was CVPR 2021. I think this is a brilliant work that they used neural rendering technique. Of course, everything has to be run on very beefy GPU, and even on a very good GPU would probably take hours to pass a sequence. But with the power of neural rendering, with and some like input masks of those layers, now there's a very reliable technology that can really decompose a video into layers, right? Layers not only in terms of mask, but really alpha matting, right? You have this continuous value alpha mats that can blend foreground and background. Right, so here, right, you can see on top left is the input video, right? And top middle and top right are the input masks using RCNN. So you can see those are not that reliable, but it gives a rough estimate of the object shapes and how they move. And then running through this OmniMat, right, you get very clean reconstruction of the background shown on the bottom left. And those two layers, right, beautifully at the bottom, middle, and also right. What's interesting here is you can see the shadow of the person, right, is not entirely visible, right, in the input. It's actually occluded by the dog, right? So it's occluded, for example, in this particular frame. But the neural rendering was, and across all the frames was able to reconstruct the shadow, right, even when it was occluded. And I think this is really cool, and this is exactly what Ted had. Ted, you envisioned probably 30 years ago how we should have done, layer decomposition. And thanks to the progress in neural rendering and in hardware, right now this is a reality. And there's some more results of OmniMat. If you're interested, feel free to check the website, and just a lot of very, very fun results. So just coming to this topic, right? So, whenever it's in computer vision, you talk about layer, people feel like this is kind of a niche topic. That's because that's not the mainstream, flow estimation, motion estimation method. But I think this paper actually changed it, right? Because this is work that I did when I was at Google with Daqing and Varun and Bill and a few others, where we were thinking how we can train the best optical flow, right? Because nowadays in the deep learning era, everything has to do training data. We have to get training data. But when you need to train a good flow, it's hard to label flow, right, for in the real videos. So we're thinking, can we, because then that's why in optical flow, typically people get, synthetic data sets, right? But synthetic data set is difficult to obtain. You need to get all the rendering pipeline set up, 3D objects, and why do you, for example, what's the most common one is called flying chairs. Why flying chairs? When you learn something from flying chairs, it's going to do a good job of inference, right, for people walking around and for cars. We have no idea, but somehow it works. Right, so we're like, can we really investigate into this and find the optimal way of generating the synthetic data set, right, that we can train networks. And again, we use 2D layer model, right? We just say, okay, because 2D layer model is in many ways is simple and intuitive. So we just grab some random images and synthesize some random motion field as background, and then we just add some objects, right? This is exactly what TED did 30 years ago, right? We followed the same idea, and we generated this something called auto-flow data set, right? That we are able to generate, this kind of, I don't know, it doesn't look that realistic, right? Because there's a, augmentation to be able to make the data set very reliable. But that's the images that we generated using this simple 2D layer composition, and that's in the first and third row. In the second and fourth row, you see the corresponding flow fields, right? That and those are the training data where we throw into networks and train flow field. And just to compare, right? Those are the flying chairs. Flying chairs from the imagery sense, it probably looks a little bit more realistic. But when we use them to train flow field, we found actually that using the same network structure, right, that trained on our data set, the auto-flow data set, we were able to get better flow field with lower error rate, right? So this shows that, of course, right? So there's the two parts: the way to generate this synthetic data set, and also the optimization, right? We're able to optimize the parameters for generating this data set. That's why we're able to push the error rate to be very low, to be even lower than the network trained from the flying chairs. So, and you may ask, what's the future, right? What's the future for layers? And I think layers still have a bright future, and probably even more so looking forward than looking backward. Recently, I've been working at Microsoft, working on foundation models, right, such as Florence. We're able to get some open world image recognition engines. And here, right, so what you can see is we get some bounding box proposals from this video, and we can do captioning for those bounding boxes, so that we can actually try to understand what each bounding box is about, right? So you can see it's actually describing, right, the cheetahs on top of a jeep and the people and so on, right? I think there'll be, and this is one where cheetah jumps from a vehicle that is in the field, right? That's how it describes this cheetah, right? So, and I think there will be, I think moving forward, there's that kind of semantics, right? We're working together with layer decomposition, and I think pretty soon we're going to see this kind of, very fine-grained layer segmentation with semantics, right? And the computer is going to describe what's really going on in the scene, and also to be able to separate them, right? And also probably remove them. And that's it. Thank you so much, Ted, for your vision for our field.
Thank you, sir. We're a little behind, but maybe one quick question if there's one. Okay, thanks. Oh, thanks, sir.
Okay.
Oh, Renjun has a question, sorry.
So for the motion augmentation part, I wonder how precise it is. So for example, can you use that for like civil engineering, detecting whether a bridge or a building is failing, going to collapse in a few years?
Sorry, I just couldn't hear. I guess because of the mask.
Okay, so for the motion augmentation project, so I wonder how precise is the motion magnification? So can you use that for precise measurement of the motion of a building, like a bridge, about when they are going to fail?
Right. So I think for our project, that was really for fun. That we're trying to just see this effect. I think Mickey and Bill, they had following up using it's kind of an Euler representation for motion, and there was like for measurement and for lots of scientific research and applications.
Thanks.